Brace yourselves for the Biostatistics, Epidemiology, and Research Design Core Special Topics Talk number 2, Generalized Linear Mixed Models for Everything. I'm Dr. Mark Williamson on behalf of DaCCoTA. Through this talk, we'll be examining generalized linear mixed models for a variety of uses in statistics. But before we get into that, we should ask the question, why do we care about statistics? Well, statistics could be defined in a couple different ways. The more formal way would be using mathematical methods for inference, estimation, and prediction of collected data. However, how I like to approach it in a more pragmatic way is statistics is using mathematics to help discover and tell the truth about the world. And I think this approach is useful because statistics often gets a very bad rap. For example, Mark Twain famously intoned that there are lies, damned lies in statistics, implying that statistics are often used to tell falsehoods. In fact, that can certainly be the case. People have often used statistics misleadingly or downright falsely. But the ideal with using statistics is to not tell lies but tell the truth through numbers, which is why it's important to both know what you're doing in statistics and to be able to clearly present it. Hopefully through this talk we'll be able to do both. So moving on a little bit into how statistics has been done and why this approach I'll be showing today is useful. So the old way of doing statistics, especially back up to a century ago, it was either by hand or with very limited computing. Things of t-tests, ANOVA, and so forth. And when you think about the data used, if the response for the y variable was not normally distributed, that is, it wasn't parametric, really the only things you would do is either try to make it close enough through some sort of transformation of the data, or you'd run a non-parametric and less powerful test. However, in the more modern era, there's a newer way of kind of approaching or thinking about statistics. Given that we have a lot more understanding, a lot more research, and mathematics has gone into statistics, and we have vastly more computing power. I mean, just think about all the computing power in your back pocket with your cell phone. We can flexibly fit a vast range of data types using a unified framework. So instead of thinking about statistics in sort of a test-based way, we can think of a more unified framework of a big model that contains all the smaller, more specific models in it. Let me visualize what I'm trying to get at here. A lot of times the first test we learn about is a t-test, looking at, say, the difference between two groups. You know, are males and females, do they have different height? Something like that. But really, a t-test is just a specialized case of a more general test, an ANOVA, analysis of variance, which looks at differences between three or more groups. T-test is really just a special case where there's only two groups. But really, ANOVA is just a specialized case of a more broad model, a linear model, in which ANOVA, the variables, the x variables are strictly categorical, where that's not the case in a linear model. But again, a linear model is really just a specialized case of either a GLM, a generalized linear model, or a GMM, a general mixed model. And last, and again, those are just special cases of an even broader model, a generalized linear mixed model. So the approach I'll be showing today approaches all these tests through the same framework, a generalized linear mixed model. So what are GLMMs? So they stand for Generalized Linear Mixed Model. And really, it's a model that allows for both non-normally distributed response variables, those Y variables. That's where we get the generalized from. And also, it allows predictor variables, those X variables, to be either fixed or random. So fixed or random effects. That's the mixed part of the model. Really, this is a mashup of a generalized linear model and a general linear mixed model. So let's define kind of some of our terms. So non-normal distributions, whereas in sort of simpler tests like t-test, ANOVA, linear regression, a lot of times there's an assumption of normality for your Y variable. Turns out a lot of data, in fact, probably most data, don't really fit that assumption. Turns out there are a lot of other distributions, ergo ways that data could conceivably be generated that fit real data much better and can be used in generalized mixed models. So for some examples are binary, binomial, beta, Poisson, native binomial, so on and so forth. So you can fit your distribution to the data rather than trying to fit the data to the distribution. And next, let's kind of define fixed and random effects. These are almost always thought of as categorical variables. Now, a fixed effect, which is found in normal like linear regression, general linear regression, it's a categorical variable which all levels of interest are included. These are usually an effect you're interested in, say maybe treatment groups or maybe different categories like ethnicity, gender, etc. Whereas a random effect is a variable in which the levels included are a subset of all levels. Other terms for this is like a blocking effect, or maybe like a location effect, where the idea is typically these random effects you're not interested in, but they have some sort of variation associated with them that you want to control for. And that you don't include all of these in your model. So maybe you have hospitals, you looked at 3 different hospitals, which are really just a subset of many, many more hospitals. So let's walk through just a couple quick examples of, say, a possible model that a GLMM would use. So say we're looking at bird eggs in nests on sandbars. We might be interested in seeing if egg counts can be modeled as a function of, say, temperature, species, and sandbar. So an egg counts might be a response variable that follows a Poisson distribution. Our temperature would be a numerical predictor variable. Our species would be a fixed effect or a fixed predictor variable, whereas sandbar, maybe which sandbar comes from, could be a random effect. Another example, maybe we're looking at disease status as a function of age, class, sex, ethnicity, and the hospital it's from. Disease status could be binary, like you either have the disease yes or don't, no. That's binary, 2 options. Age and sex, typically thought of as fixed effects. Same with ethnicity, but then the hospital, you only sample at a few hospitals out of a theoretical infinity of hospitals. That could be a random effect. Similarly, here's a third example. Maybe you're looking at someone's grade based on like 0 to 1, so like kind of a percentage. That could follow a beta distribution. And maybe you have math and reading score, which are numerical variables, but then you have your classroom in school, because those are school children. Both could be considered random effects. In fact, they could be sort of more complicated, because we could imagine classrooms are nested inside school. So you can have this hierarchical effect, a random effect that you can control for, because different classrooms are going to have different effects on the children in different schools as well. So what we'll be using today in our actual analyses will be PROC GLIMMIX. It's a procedure found in the SAS software. So this will be used in SAS. However, you don't need SAS to run generalized linear mixed models. R does just fine, as well as other common software like Stata, SPSS, etc. So the basic syntax for PROC GLIMMIX is as shown. The black are just the things you need to include, where the red are whatever your specific data is. So you need to include your data set, any sort of categorical variable are going to go in this class statement. So for example, say I have a categorical variable 1, 2, and then block. This is what I'm calling just the random effect here. Then you need a model statement where you model your y variable as a function of all your x variables. So maybe you have a numerical, 2 categorical, and this vertical bar would just show also the interaction term between these two. And then you also need a slash and then your distribution. It can be on a separate line just for clarity like here, but it could also be up on the same line here. And then you have to specialize your distribution. If you leave this blank, you certainly can. If you don't have this, it'll just default to a normal. So that's good to know. And then your random effect, if you have one, goes in this random statement here. And this is the simplest setup for the random effect, for random intercept. Now, there's all sorts of options you can add. I've shown here in blue to customize. You can estimate by different methods, add plots, do GLIMMIX by maybe say different categories, only include certain data with a where statement. In your model statement, you can add a solution table, an odds ratio table. That's especially good for logistic regression. You can include different links. You can include offsets, which is pretty common in some Poisson regressions. For your random statement, you can add, if you add in a variable like this, like category, which isn't random, you can get random intercepts and slopes, where this intercept / subject equals block, that is equivalent. These things are equivalent actually to this simplified statement here. But then you can also add, like I said, another categorical variable to get random slopes as well. Other options, you can add a covariance test, you can weight your variables, and then you can do a variety of outputs. One we'll be seeing here later is getting the least squared means of a categorical variable and then outputting them to its own data set. You can also get predicted variables, so that's more for like numerical regression, using this output statement where you get the prediction variables as well as confidence limits out. And here are some resources. Obviously, this is just scratching the bare surface. If you have a couple weekends and you want to slog through a 300+ full documentation of PROC GLIMMIX, you can certainly use it here. If you want a little quicker, more kind of user-friendly online version, you can use this link here. So today we'll be covering these different tests using our generalized linear mixed model framework. Cover t-tests, ANOVA, linear regression, Poisson and logistic regression, which are forms of a generalized linear model. We have then our mixed model, and then we'll look at the generalized linear mixed model proper. Without further ado, I present to you generalized linear mixed models for everything. Does not include categorical data, non-linear advanced methods can sync, often not available in all statistical software. Messaging data rates may apply, void where prohibited. We'll begin our approach with the classic t-test. In SAS, we'll be using the dataset sashelp.class. This is a dataset included in SAS, which has the name, sex, and height of 19 students. And the question we want to answer is there a difference in height between boys and girls? So to do this in SAS, kind of the old-fashioned way, you do a PROC t-test, where class is your sex, that's your categorical variable, and your numerical variable, your y variable, is height. Pretty similar setup in GLIMMIX. We have class equals sex, and then however you have a model statement where you actually have to more or less write out your equation, so height as a function of sex. And then you can include a solution, and then I include here the distribution is normal. Again, that's the default, so if you nix this, it would come out the same. And then additionally, we're going to add a little more complexity here by getting our least squared means into a new data set, then using this PROC SG plot. This is a standard way to create many plots in SAS. We're going to use this data set, and we're going to have a vertical bar chart, which is with using parameters. So that's our means from our PROC GLIMMIX, with sex as a category, and then a response as an estimate, and then with an upper and lower confidence intervals. And you can print out this class least squared means if you want to see what these things are called. So the estimate, upper and lower. So here's the results. We have our t-test to the left here, and our PROC GLIMMIX to the right. Let's start with the t-test. So first of all, we can get out here our different means of height between males and females, and we see here already looks like males are taller, 63 instead of 60. These are probably centimeters, or sorry, inches. But the question is, are they significantly taller? So one thing that t-test does is it does this equality of variance test down here, because one of the assumptions is equality of variances with a t-test. If they aren't equal, you can do a slightly less powerful test, which we'll see. So what equality of variances does is it tests the null hypothesis that variances are equal between males and females. And it gives a test statistic in the F value here, and then the p-value. And so this p-value is not smaller than 0.05. In fact, it's much larger, which means we fail to reject the null. So we assume that the equality of variances, or that assumption, is upheld. So we can use, therefore, in these output methods, these results, you can use the pooled method, which assumes equal variances. We find our test statistic in the t-value and our p-value. We see here that the p-value is not significant, which means that our test did not find males and females to be different. Now let's move on to the right. This is the GLIMMIX procedure. You can see it spits out quite a bit more. And for this first test here, I included everything that GLIMMIX provided. In the future, I'll just provide the different tables that are relevant. So does our response variable is height. You can see that our class is sex. And a big thing that GLIMMIX always provides, which I really like, is fit statistics. And the one to note here is this Pearson chi-squared over degrees of freedom. Just really tells how well the model that we use fit the data, especially the distribution. Now, typically this Pearson chi-squared over degrees of freedom should be about 1. If it's much greater than 2, you typically want to try to find a better distribution, a better model. Obviously, you see this is quite large. So if I was doing this for real, I'd probably play around with this. But for these examples, really, I'm just trying to show the difference between the t-test and the GLIMMIX, or in fact, not so much the difference, but the similarities. So we'll leave that off for now. But getting to the results, you can see here again, we get the exact same sort of means between the two, as well as the same t-value and p-value. That again, the exact same shows us we're not significant. Now, a big thing that GLIMMIX will always show us these type 3 tests of fixed effects. You can see here we have sex. I usually look at the type 3 test first and then go from there. You can see it's giving slightly different things than our parameter estimates. This gives a t-value, this gives an f-value. They're a little bit different, but as you can see, the p-value is the same. So I usually check type 3 test of fixed effects. If the p-value is not significant, I don't move on. If it is, I look further. So there we go. Now here's some graphs here, because we see here on the left, this is default for the t-test. It gives you distributions and some QQ plots, which is good for looking at how well your model fit. And then these are the graphs I specifically made in PROC GLIMMIX. You can see here that while males are taller, it's not significant. In fact, the tallest females, are even taller than the average male. So next, let's look at ANOVA. We'll be using the dataset B weight, which includes infant birth weight and mother's education level. And we'll treat mother's education level as a categorical variable. We want to ask the question, is there a difference in birth weight across educational level? So the old way would be to use PROC ANOVA, set mom's education level as a class, and then model weight as a function of education level, and then have a mean statement with the education level. PROC GLIMMIX, very similar, class, model statement. You can add your solution and your normal distribution, and of course get LS means, output that, and then use that in PROC SGplot to get graphs. So here are some results. On the left, ANOVA procedure. First thing to note, we have our class level information. We see there's 4 different levels. Education level range from 0, 1, 2, and 3. These probably indicate things like no high school diploma, some college degree, something like that. Other things of interest is we get our some summary statistics of different education levels, the number as well as the mean. These weights are probably in grams. It looks like such large numbers. And then we get our test statistics for the model. We see that there's a pretty high F value and then a very significant P value. So it looks like weight of newborn infants is different across at least one educational level. Again, we get the same thing here. Now, normally then, of course, with significant ANOVA results, you would do some sort of post hoc test. I'm not showing that here, but that's where you would go on. Now, PROC GLIMMIX, gives you the same sort of information. Get the class levels. We get one thing ANOVA doesn't do is our chi-square degrees of freedom. We see that this is pretty high, so in other circumstances, I would probably find a better distribution, better model. But here again, I'm just trying to show how we can essentially replicate the ANOVA procedure with the GLIMMIX procedure. So again, here's our estimates of weight, mean weight across education levels, and here's our test statistics. You can see that these give the same results, and so forth. So moving on to graphs, this is what PROC ANOVA automatically generates, which is kind of useful. It's pretty messy here given the spread of data for birth weight across educational level. This is the graph I specifically made using PROC SGplot, and we can see here that looks like women with education level 2 have the highest birth weight, and it looks like education level 3 has the lowest. Okay, let's turn to linear regression now. We'll use the dataset BMI men or BMI men. It includes BMI, body mass index, and age for a variety of men. And the question we want to ask is there a relationship between body mass index and age in men? So PROC reg would be the tool of choice in kind of the old schema. You just have a model. BMI is a function of age. PROC GLIMMIX is very similar. almost identical. In fact, though, we can add solution and then our distribution, which is, again, for this example, normal. Again, we'll do output, and this time, instead of LS means, we do this output function out, and then we have our predicting variables, as well as lower and upper confidence limits. So we can plot this on a scatter plot. And then we can have a scatter plot, a band with the confidence intervals, a scatter, so those are our actual raw data, and then the series, that line of best fit using our predicted variables. So here are results for PROC reg. Look at our model, our test statistic and our p-value. Looks like there's a significant relationship. And again, this is the overall model. This is the specific age specifically in the model. The p-values are going to be the same. However, the test statistic is a little bit different. This is a t-value, or this is an f-value. Look at the GLIMMIX. We have our fit statistics, but then our parameter estimates, as you can see here, are the same, both for the overall model and then for age specifically. We can see that we're getting the exact same results. Now, for graphs, there's a lot of really nice diagnostic plots that PROC reg does, including this sort of panel, and then it has a nice fit plot and then residuals. And then we've essentially replicated using PROC SGplot the fit plot. We see that as age increases, looks like BMI increases as well, though it's not particularly strong. Okay, let's turn to generalized linear models now. The first being a logistic regression model. So logistic regression is when your y variable is either binary or multinomial, so it's not continuous. So we're going to use birth weight. This is another data set. It includes infant birth weight in a binary fashion, so it's either a low birth weight, it's either yes or no. So this is a little bit different data set than we saw before. Then we have marriage status, age group, and race. We're going to ask the question, does marriage status, age group, and race help predict the probability of having an infant of low birth weight? So we can use PROC Logistic, setting our married, age group, and race all as classes, and then modeling low birth weight. And then we can specify which probability we want to model, whether we want to probability model yes or no. It will default to one of these, though I always like to explicitly state what I want to do here. And then these are as function of our categorical variables. PROC GLIMMIX is very similar. However, we can include our solution. We actually can include an odds ratio, which is very useful for logistic regression. And then now, for the first time, we're going to set our distribution to a different distribution than normal. This is going to be a binary distribution because we know that low birth weight is binary. It's either yes or it's no. There's no in between. So taking a look at our results, starting to get a little bit more here. But for the logistic procedure, first of all, we can see our response profile, whether there's no or yes birth weight. And it's always nice to see this little text here that tells us what we're trying to model. So we're modeling the probability that low birth weight equals yes. We, of course, could do probability of low birth weight equals no, and everything will kind of be reversed. So it's really important to know what you're actually modeling. So it's a little hard to see here, but this does give some fit statistics, though not the same as GLIMMIX. These mostly can be used for comparing similar models between each other. Then here are our analysis of effects. Looks like marriage, age group, and race, they're all significant. We got our Wall chi-squared, so this is different from a t-test or f-tests, and then the probability. Similarly in GLIMMIX, we have our response profile and then our fit statistics, and we can see here, this is a perfect fit because our data is perfectly binary. So this was using a binary distribution was a good choice. And now we get type 3 fixed effects. Now this is where we'll see a little bit of difference between the two. While the p-values are both identical here, they're actually giving different test statistics here. So these are F values, which don't quite line up with the Wald chi-square values. The marriage one looks like it does, but the other two are a little bit off. So that is an important difference there. They're using slightly different test statistics. But the overall results of significance look to be the exact same. We'll look here at regression tables because plotting isn't really relevant here or useful for logistic regression. We typically look at odds ratios, which we'll do here. So we're trying to model the probability of having a low birth weight. So what an odds ratio table does is for each categorical variable, it compares one of the categories to all the other categories to give the probability of this outcome. And so gives an estimate. And so an estimate of 1 would mean there's the exact same probability between the groups. Higher than 1 means that the group in question has a higher probability, lower than 1, lower probability. So for example, those who are not married compared to those who are married, they have a lower probability of having low birth weight child. And then the confidence intervals tell you whether they're significant. Since this doesn't overlap 1, this is significantly lower. It has only about 3/4 as likely. And if there are more than 2 categories, it'll compare, do multiple comparisons. So for age group, there's 3 age groups. So compare age group 1 versus 3 and then 2 versus 3. And similarly for our various races. And then we got the same sort of odds ratio table out in PROC GLIMMIX using the odds ratio term. You can see here, there's either point estimates, they're going to be the same here, as well as the confidence intervals. And we take a look here, all of these are significant except for the 2 I've shown in red, because if we look at Asians compared to whites, they have a higher probability of having low birth weight, but the confidence intervals include 1, so that means it's not significant. Similarly, Native Americans have a lower probability, but again, that encompasses 1, so that's not significant. Okay, so another kind of generalized linear model is Poisson. And so we'll be using this Poisson.SAS7b DAT dataset. This is not included in SAS, but you can get it from this website here. And this includes days absent from the school year. So that's our Y variable. Math standardized tests, language standardized test score, and then gender. And so we're going to ask is whether math scores, language scores, and gender helps predict the number of days absent from school. We can use PROC GenMod for a generalized linear model. We'll model days absent as a function of our 3 numerical variables, or sorry, not 2 numerical and 1 categorical. And then we'll have to include a link function and a distribution of Poisson. If you don't include this function, it should still work because log is the default link for Poisson, so it should include that. And we have virtually the same setup for PROC GLIMMIX. So here are results. One nice thing with the GenMod procedure is it actually involves a Pearson chi-squared fit statistic like the GLIMMIX. And then now we have our maximum likelihood parameter estimates. And so since these are all numerical or sort of quasi-numerical variables, how to interpret this is these are estimates of our intercept are 2 numerical, and then females technically sort of kind of blocked off as sort of numerical, even though it's categorical, where female, 1 equals female, 0 equals male. And then this estimate is based on setting female to 0, so to male. And then, of course, we have our test statistic and p-values. And looks like they're all significant except for math. Looks like that's not significant. It's on the verge. PROC GLIMMIX, very similar, same chi-squared. Same estimates, though, again, they have different t-values here, different f-values, because it's not the same statistic. However, if you look, the p-values, regardless of where you look, are going to be exactly the same. And so let's interpret this a little bit. So math and language were similar, but math was not significant. But if we look at language, so this is a negative estimate, which means there's a negative relationship between number of days missed. So remember, that's our response. So it looks like as your language score goes up, so the better you do in language, the number of days absent goes down, which kind of makes sense. If you're doing better at school, it's likely going to contribute to missing less days. Math, same trend, though we can see that it was smaller. So this is like our slope. These are our slope. It was smaller and it was not significant. Now female, what this is saying here is, so this is setting at fixed variable of male, and which means is that estimate for males, if you're male, is about half that as a female. So turns out that females are almost twice as likely, when everything else is held equal, to have days absent, or twice as many days absent from school, which is actually kind of a surprising result, because you think maybe males would have more, but that's not what it is showing. And then, in fact, I went in, and you can do this yourself. You can look at the mean number of days missed between males and females. You can see that females on average have more days missed. Next, let us consider the linear mixed model. We'll be using data subplot from this address here. It includes block, which is going to be our random effect, a whole plot factor, and a subplot factor, and yield, so our y variable. So the whole plot factor could be something like, say, irrigation, or a subplot factor would be something like a variety of our whatever crop we're planting. So we're going to ask the question, is yield different across a whole plot factor and subplot factor while controlling for blocking? So we can use PROC mixed for a mixed model, where we have our class statement having our A, B, and block. And then our model is going to be this y is a function of A, B, and then, of course, the interaction term. We could simplify this and just do A, B. That would be a condensed way of doing it, but either way will work. And then our random effect is going to be a little more complicated than the basic. We're going to have block as a random effect, but then also the interaction of our whole plot factor and our block as an effect. For PROC GLIMMIX, other than the fact that this is GLIMMIX and this is mixed, the format are exactly the same. You can kind of see a pattern here as we get more and more complex statistical models. These other procedures more and more mimic this more general and flexible model. So we got results here. This spits out a lot, so bear with me. So now that we're looking at these more complex models, you can actually set different estimation methods. I think the default is this restricted maximum likelihood. So show what you have here that's useful in case you need to use other estimation methods. Class level information, looks like we have 3 levels in our plot wide factor, and then 2 and B, so the 2 different varieties, and then our block, so with 4 different blocks. Here's our covariance. So now we have random effects, and essentially we want to treat them as random effects, help draw out variation, kind of correct for it, so we have more power sort of to detect our things we actually care about, say our varieties, our B. So this covariance parameter estimates show that block has the most covariance, followed by the interaction, and then the residual. So these are pretty high numbers, which show that it was sort of reasonable to include these as random effects. We got our type 3 test of fixed effects, and what we can see here is looks like only B is significant, A and their interaction is not. So there is a difference in yield between those 2 different varieties, those 2 different Bs. And we can see in the GLIMMIX, same sort of thing. We can get estimation techniques, class level information, fit statistics, covariance. Now we can see that they're the exact same here. And then this also gives us standard error. Type 3 test of fixed effects. We can see again only B is significant. And then we can also get our solution and look at random effects solutions if we really want to. Alrighty, we finally made it to actual dyed in the wool, straight no chaser, generalized linear mixed models. We will use the data set from this website here, which includes hospital center, treatment group, total number of individuals, and the number of individuals with side effects. So we want to ask the nuanced question, is the proportion of those with side effects different between treatment groups while controlling for hospital center? So this is our fixed effect, this is our random effect, and this proportion of those with side effects, that is our non-normally distributed Y variable. So in PROC GLIMMIX, we can set center and group as classes, model. Now this is interesting since we're looking at proportion. We actually have 2 different variables, side effect and total number. We can have a slash, this format here, side effect slash n. So that's our setup, and PROC GLIMMIX will recognize this. You could, of course, create a new variable where you just take side effect divided by the total number, but it's nice that PROC GLIMMIX will recognize this. So this will give us a proportion of side effect over the total number. We'll do this as a function of group, the solution, and we don't need to have a distribution because it knows, because we have the set up here, what distribution it is. And then we'll have our center as random, and then we'll get LS means and output and so forth. And then this is our PROC SG plot from those means. So that here are results. There's a lot going on here, so bear with me. So first of all, one thing is it knows that this is a binomial distribution because we had that event trial setup. And it gives us class level information. We see that we have 2 groups, treatment and control, and then there's random effects of different centers, and we have 15 different ones out of a possibility of many more centers. Our chi-square degrees of freedom looks pretty good. And then here's our covariance. This is interpreted a little bit differently than what we saw before, but essentially this is still positive, which means there is some covariance so that there's variation in the center number that we can account for using this model. And finally here we have our effective fixed effect of group, and that is significant. And so we can see here, and I've plotted this, that group A has a lower proportion of side effects than group B. So I believe group A was the treatment and B was control. All right, there you have it. We've walked through a series of common statistical tests and comparing them in a separate procedure to GLIMMIX, and we'd see for all the cases almost the exact same result, showing us that we can pretty much use generalized linear mixed models for any of our standard statistical tests. Now, unfortunately, well, I did say it is for everything, and actually, can't do the kitchen sink and a few other things. So some notable exceptions: it can't do categorical only data. You'll need to do some sort of PROC frequency. Once again, these are still linear models, so if you want to use nonlinear models, you have to use something like PROC nonlinear. And then one specific assumption about generalized linear mixed models that we didn't quite go over is assumption is that the random effects come from a normal distribution. It's kind of nuanced, but essentially if that's assumption is not met, you have a hierarchical model with normal random effects, you can use a more complex model for that. And of course, another thing you can't do is specialized advanced models such as, say, structural equation models, principal components analysis, etc., that have really specific goals and requirements. But really, other than that, any sort of regression style analysis you can pretty much do with PROC GLIMMIX. So with that, thank you for joining me today. Hopefully this helped. This was supported by the DaCCoTA grant from the NIH. This is our award number. So if you found this useful, helpful, please reference us. That would be great. All right, have a great day, and thank you.